In this mechanics physics question, we have Newton's laws, both explanation and calculation questions. There's also a bit of SUVAT in here as well. So we have a jet engine. Air enters the engine at A and is heated before leaving B at a much higher speed. State what happens to the momentum of the air as it passes through the engine. So whatever mass enters the engine must be leaving the engine every second. If we don't have the same mass going in as going out, so let's say there's a scenario where there's more mass going in than there is leaving, then that means that the engine will be, over time, consistently gaining mass, which doesn't make sense, which wouldn't be happening. So whatever mass goes in is the mass going out. And if the speed of the air is increasing as it leaves the engine, that means the momentum must be increasing. Mass is constant, P is equal to mv. If the speed increases, momentum increases. Explain, using appropriate laws of motion, why the air exerts a force on the engine in the forward direction. Okay, so the air is experiencing a change in momentum. Newton's second law is that force is equal to rate of change of momentum. So if the air experiences a change in momentum, it must experience a force. From Newton's third law, if the engine is exerting a backwards force on the air, that means the air exerts an equal and opposite forwards force on the engine. For 1.3, we're told that in 1 second, a mass of 210 kilograms enters the air at A. So this is how much mass enters per second. I'll write that as m divided by delta t. That's like the rate of flow of mass. That's equal to 210 kilograms per second. The speed of this mass of air increases by 570. So that would mean that the change in velocity, delta v, is equal to 570. Calculate the force that the air exerts on the engine. So force is equal to rate of change of momentum. Change in momentum is the final momentum minus the initial momentum. I'll factorize out the mass, so m times Vf minus Vi. And then I can write this as m over delta t multiplied by the change in velocity. So we put everything in, 210 multiplied by 570, and that gives 119,700, or 1.20 times 10 to the 5 newtons. For 1.4, when the aircraft lands, the jet engines exert a decelerating force on the aircraft by making use of the deflector plates that we see over here. These cause the air leaving the engine to be deflected, so the air leaving the engine is deflected at an angle to the direction the aircraft is traveling, as shown in the figure. So we see the air comes in this way, it gets deflected like that, the aircraft is moving forwards. The speed of the air leaving B is the same as the speed of the deflected air. Explain why the momentum of the air changes. Okay, so momentum is equal to mass times velocity. Momentum is a vector, as velocity is also a vector. So even if the speed doesn't change, if the direction changes, as we see here, the direction of velocity is this way to begin with, and now is this way. If the direction of the velocity changes, then that means velocity is changing, and therefore momentum is also changing. The total horizontal decelerating force exerted on the deflected plates of the engine is 190 kilonewtons, and then we're trying to work out the deceleration. We're given the mass, so the mass is 7 times 10 to the 4 kilograms. The force, 190 kilonewton, so that's times 10 to the 3. And then we can just use F is equal to ma. Acceleration is then force over mass. Put these two things in the equation. and we end up with 2.71 meters per second squared. So for 1.6, we're told the aircraft lands on the runway, traveling at a speed of 68 meters per second, with the deflector plates acting. Calculate the distance the aircraft travels along the runway until it comes to rest. Okay, so we're trying to work out a distance. We're given an initial speed of 68. It comes to rest at the end. We're told in the last sentence that the decelerating force is constant. So then that would mean that the acceleration is constant. That's the same deceleration that we had before, minus 2.71. So I'll write that to more decimal places. So minus 2.714. And we're not told anything about time. So with these three, we can use v squared is u squared plus 2as. Rearrange for s, that would be v squared minus u squared over 2a. Sub everything in. 0 minus 68 squared all over 2 times minus 2.714. And that gives us a distance of 850 meters. For the final part, suggest why in practice the decelerating force provided by the deflector plates may not remain constant. Well, as the speed of the aircraft changes, there may be less air coming into the engines. As it slows down, there might be less air coming into the engines. If the mass of air going into the engines has decreased, so mass goes down, remember that force is equal to rate of change of momentum. And we were considering this equation, or this variation of it, mass over time, which is how much mass comes in per second, times whatever the change in velocity is of the air. If this whole quantity, the mass per second, goes down, then the force will decrease.